Today we're looking at section 7.4, day 2, logs and the inverse logarithms. Yesterday we looked at two special log properties. Log base b of b is always equal to 1, and the second one was log base b of 1 is always equal to 0. Now we're going to add in two new properties. The next one is log base b of b to the x will always equal x. If your log base and the base of the next value are the same number, your answer will always be whatever you see in that power position, x. And the fourth one, b raised to the log base b of x will equal x. So again, if your base here and your log base are equal to each other, your answer is just what you see right there in the power position, x. Over on the side, we've got some samples for each of these. First one, 10 raised to the log of 4. Now this doesn't exactly look like one of our properties, but if you remember on this first one, that if you do not see a log base, you must assume that you are in base 10. So now we actually have number 4. 10 raised to the log base 10 of 4. Your base values both match, which means your answer is just 4. 5 raised to the log base 5 of 1/4. 5's match, answer 1/4. E raised to the natural log of 9. Remember, natural log is really log base e, so yes, you match. E raised to the log base e of 9. Your answer is just 9. Log base 7 of 7 equals 3. That's property number 3. Base values match. Your answer is 3. Log base 5 of 25 to the x. Well, we can't just say x right now because our 5 and our 25 don't match. But we can make 25 come from 5's. Log base 5 of 5 squared to the x, which is really log base 5 of 5 to the 2x. Now your log base and your value match, so your answer is just the power, which is 2x. And the last one here, log base 3 of 27 to the x. We can make 27 come from 3's. Log base 3 of 3 to the third, and then raised to the x. Log base 3 of 3 to the 3x. Now your base values match. Your answer is the power 3x. What we're going to work on today is finding the inverse of the logarithm and then graph that inverse. Your first step is the same as when we were going to try to find any inverse equation. We swap letters. After we swap letters, we resolve for y. Now when we resolve for y, we will probably have to get, we'll probably have to use either the logarithm or exponent rule to solve. So if you have something that's in log form, you'll probably need to take it back into exponent form. Or if it was in exponent form, you maybe have to write it in log form in order to be able to solve. Your first example, y equals 6 to the x. I want to try to find the inverse equation. So the first thing we do is swap letters. X equals 6 to the y. Now I have to try to resolve to get y by itself. Y is currently in the power position, and to get it out of the power position, I need to use logs to solve that. This is your base, your 6 is your base, so it will be log base 6 of x equals y. Log base 6 of x equals y. We now have y by itself. So, since we can write that last line, log base 6 of x equals x, y equals 6 to the x, and log base 6 of x are now inverses of each other. What we were writing was the inverse equation. 6 to the x and log base 6 of x are inverse equations of each other. Let's try number 2. Y equals natural log x. Now remember, natural log x really means log base e. Okay, so the first thing we do is swap our letters. X equals natural log y. Now this one is in log form, so I have to take it out of log form and put it into exponent form. That's why I need to know that natural log is really log base e. What I then have is x equals log base e of y, and I can now change that from log form into exponent form. Your base is e, so it becomes e raised to the x equals y. We now have y by itself, so this is your inverse equation. Y equals e to the x. So natural log of x and e to the x are the inverse equations of each other. Let's try these two. We'll find the inverse functions. Y equals 8 raised to the x plus 1. Step number 1 is always to swap your letters. X equals 8 raised to the y plus 1. Now I have to try to get the y by itself. You notice the y is up in the power position. So to get it out of the power position, I need to use logs to solve. 8 is my base. Log base 8 of x equals y plus 1. I almost have y by itself, but I need to move the 1, so I'll have log base 8 of x minus 1 equals y. There's your inverse model. Your second one, y equals log base 3 of x minus 4. The first thing we do again is swap our letters. X equals log base 3 of y minus 4. Now this one is in log form, so to solve for y, I have to take it out of log form and put it into exponent form. 3 is my base. 3 to the x equals y minus 4, and then just move your 4 to the other side. 3 to the x plus 4 equals y. So my dad was a track coach at Mayo High School for many, many years, and he liked tinkering with track apparatus, and one of the things that he designed was the hammer throw ring. So if anybody's familiar with field events, discus, javelin, shot put, hammer throw is an event that is college and Olympic sport. He designed the Olympic ring that ended up being used at the Atlanta Olympics in 1996. And I was lucky enough to be able to go along with him and watch all of the track and field at those Olympics, and we were able to see his hammer throw ring used in Olympic competition. It was extremely exciting for him and all of us in our family. Next, we're going to look at how do we graph the log function, and then how do we graph the inverse log function. So remember that log base b of x and b to the x are inverses of each other. We just showed that in a couple examples. If you know what the log base is, we can use the go-to points from that, because that's going to be in exponent form. We can use those exponent form go-to points, and then we can use those points that will help us try to graph the inverse graph. So, a few steps, and you definitely need to write these down in your notes. The first thing you need to notice is, what base are you in? After you know what base you're in, write the go-to points that go with that base. Now if you're graphing the inverse, anytime we do an inverse, we swap letters. So if we know the go-to points for our base, we can swap those go-to points. Those two go-to points will then represent the inverse equation. Once we've swapped our go-to points, we can then start doing our shifts. And our shifts will be the exact same A, H, and K as we have done in the past. Since we are doing an inverse model, everything that we now have done in the past will now be switched. Your asymptote line for the exponent graph will now switch to be a vertical line for your logarithm graph. And your domain and range will also switch from what we're used to with the exponential graph. Those will also switch as well. So instead of seeing the domain as all reals and the range as y greater than 0, those now swap. The domain is now x is greater than whatever our h value is, this number. And our range will now be all real numbers. Okay, so definitely get this list down, and then we'll try to talk through a few samples. First one, we're going to try to graph y equals log base 4 of x. So the first thing I mentioned was we need to know what base we're in. We're in base 4. Base 4 comes from the exponential graph 4 to the x. We need to use the go-to points that belong to 4 to the x. Those go-to points, think exponential growth now, 0, 1, and 1, 4. Since we're in base 4, we're going to use 1, 4. Now, we're not graphing the exponential, we're graphing the inverse of the exponential. Inverse means switch the letters. So we need to swap 0, 1 into 1, 0, and swap 1, 4 into 4, 1. This is what we will then plot and do any shifting if need be. Well, if you notice, there's nothing here with your x, so there's no h. There's no a value in the front as a multiplier. There's no k value in the back. So we have no shifts to take place, which means these are the only two ordered pairs that we need to plot. 1, 0 and 4, 1. Now remember, the typical exponential graph goes this way with a horizontal asymptote line. Everything is now shifted. So when we graph our two dots together, instead of being slow rise going up, your picture now starts from the bottom, picks up your two go-to points, and goes out. The asymptote line is no longer horizontal, it is now vertical. And your vertical asymptote line comes from what you see on the inside, the h value. And since we had no h value, we assume 0. So our vertical line is up and down in green here at x equals 0. And then we can write our domain and range. Our domain will be all x values greater than 0, that same h number. Our range is now all real values. And our asymptote line, as we said, was at x equals 0. Everything switches. Domain and range switch, asymptote line switches. It's no longer y equals horizontal, it's now x equals vertical. Next one, log base 5 of x plus 1. We have one shift going on. First we notice what base we're in. We're in base 5, so it came from 5 to the x. Those go-to points are 0, 1, 1, 5. And now we shift. Inside with the x, it says plus 1, I need to subtract 1. 1 subtract 1 is 0, 5 subtract 1 is 4. I have no a value in the front, so I don't multiply, no stretch. And I have no k value, so I don't have to add in anything in the back. So these end up as my ending points. 0, 0, 4, 1. Remember, the shape of your graph starts low, picks up your dots and goes off to the right. Your vertical line is now what you see on the inside. Our vertical line said plus 1, we say minus 1. So our vertical line is at x equals negative 1. That's the green line that I have drawn here. And your domain matches that vertical line. X is greater than negative 1, and the range will always be all reals. This next example has all three shifts. 2 times log base 2 of x plus 3 plus 1. This graph is in base 2, so it came from 2 to the x. 0, 1, and 1, 2 are your go-to points. Now I do my shifting. My x value says plus 3, so I need to subtract 3. 1 subtract 3 is negative 2. 2 subtract 3 is negative 1. My y value. First I multiply by 2, then I add 1. 1 times 2 is 2. Oh, excuse me, 0 times 2 is still 0, and 0 plus 1 is 1. 1 times 2 is 2. 2 plus 1 takes me to 3. My ending points are negative 2, 1, negative 1, 3. Your curve starts on the low end always, picks up your two dots and then goes off to the right. Your vertical asymptote line matches the opposite here, negative 3. And your domain matches your asymptote line. X is greater than negative 3, range is all reals. Last one we're going to do is question number 52. This is from your assignment. I thought we could work this one together, make sure everybody is okay on this one. G of x equals log base 6 of x minus 4, and then plus 2. First you need to know what it comes from. That's going to help you with your go-to points. So check your base. What base are you in? That means this came from 6 to the x. So those original go-to points, 0, 1, 1, 6. Now swap your go-to points. 1, 0, 6, 1. Now we shift those points. We've got inside, we've got x minus 4. That means we're going to add 4. 1 plus 4, 5. 6 plus 4, 10. We're done shifting the x-coordinate. Now we shift the y values. I do not have a multiplier, but I will have to add 2 to each of my x-coordinates. 0 plus 2 leaves me at 2. 1 plus 2 leaves me at 3. Those should be my ending points. We'll go to our graph. What do we got? 5, 2. And then 10, 3. I don't think I'm going to fit. 5, 6, 7, 8, 9, 10. Where? 10, 3. Now before you draw in your curve, put in your asymptote line. Our asymptote line would be the opposite of negative 4, which means at positive 4. There's your asymptote line. Remember, you cannot cross that line. You're going to come close. Your curve starts low, picks up your 2 dots, and goes out to the right. We can then answer the domain and range question. Your domain will be all x's greater than 4. Range is all reals, and your asymptote line matches your domain value, x equals 4. And I believe that is it. All right, so there's your inverse graphs, graphing your logarithms, which is the inverse of the exponent graphs. We'll get that one added into our cheat sheet for your final exam, and make sure you go to Skyward and answer your 3 questions in your Skyward assignment.